Hello everyone. Today we shall be covering our 8th lecture of thermodynamics, where we shall cover open feed water heaters and closed feed water heaters. Now whenever you're running a power plant or an engine, you want to reduce the amount of energy you have to put in as possible, and you want to recycle as much of your byproduct or your waste as possible. Now, what you might not have thought about, but heat is actually a waste when used in these type of cycles. So two types of ways that people are able to recycle that heat is through open feed water heaters and closed feed water heaters. Well, first we're going to look at what an open feed water heater does. Here we have a basic open feed water heater cycle with a turbine. So water will leave from the boiler here, well, steam at this point. Steam will leave from the boiler, go through the high pressure turbine. One sec, let me label everything here real quick, actually. 5, 6, and 7. So steam will flow through this high pressure turbine, and some of that steam will be siphoned off into our open feed water heater, which I'll explain to you in a second. Then the rest of steam goes into the lower pressure turbine. Now you might ask, well, why is this a high pressure turbine and why is this a low pressure turbine? Well, with a turbine, you're taking that steam and you're producing work. Well, whenever you do that, you're removing energy from that steam, so it's going to end up causing a loss in pressure. Therefore, this lower pressure turbine is simply at a lower pressure than the high pressure turbine, hence low pressure and high pressure. Anyway, back to it. The steam that's now gone through both turbines will flow through to the condenser, where it will become liquid, and then it will be pumped into the open feed water heater. Now, this portion here that was siphoned off between the high pressure and low pressure turbine, that is still superheated steam, because remember, we're sending superheated steam into the low pressure turbine. So this superheated steam enters the open feed water heater, mixes with the liquid water coming here from pump 1, and preheats that water. Now, inside the open feed water heater, where I have this steam entering here from this area, and I have this water entering down here, this steam and this water will mix, and it'll end up cooling the steam, forming, well, more water. So everything leaves the open feed water heater as water, liquid water. Well, then this liquid water is then pumped back up to the pressure needed for the high pressure turbine, heat is added, and it re-vaporized. But the point of this open feed water heater is this steam and this water, as they're mixing and becoming liquid water, that steam is heating up the water that came out of the condenser. Therefore, I'm inputting some heat into the water here, but I'm not adding any heat from my surroundings, so I'm not burning coal or nuclear reactor or whatever. This is purely an internal process, so there's no heat added into this system here from the surroundings. There's no heat added. This is purely internal. This allows me to increase the temperature prior to going through the pump. Therefore, I need to add less heat in the boiler to superheat the water, turning into superheated steam and resending it through the cycle. So, well, to do that, I divert some, like I said, some amount of steam. We'll call that Y. Well, if Y amount of steam went through here, then I'd have 1 minus Y of the mass going through here. Now, what is Y? Y is, like I said, a fraction of it. So I could say, oh, I'm diverting 50% of the steam into my open feed water heater. Well, then Y would equal 0.5. I could say I'm diverting 30% of the steam. Well, then Y would become 0.3. That's what Y is. For this problem, since I've already gone over how to solve these types of systems in my previous video, because what I showed you last time of how to handle control volumes, you apply the exact same thing here, and that's how you're going to solve this. So I'm not going to plug in any numbers. This is going to be purely variables. So first things first, let's create our TS diagram. Like always, we should always create our TS diagram. So here we go, TS diagram. Let's make this black and TS, and then let's create our dome. All right, and now remember, we're going through here. This is going to be one pressure because we're going from our boiler to our high pressure turbine. Now this lost some pressure here, so this will be P2. Well, now I'm going through a second turbine. So when I'm coming out of that second turbine, I'm now at P3. So down here, I need to add 3 different pressure lines. Here's 1, here's 2, and here is 3. So P1, P2, P3, where P1 is greater than P2, which is greater than P3. So if you recall here, I am starting at my highest pressure and I have superheated steam. So I am over here. I'm right here. Right? Same about there. So then I go through my high pressure turbine and I go to state 2. Well, we're going to treat this as isentropic, so we're going to have no change in entropy. So assuming I can draw straight, we're going to go straight down here to point 2. All right. Now point 2, I'm going to have siphon off some steam to go through my open feed water heater, and I'm going to have the rest of it go through my low pressure turbine. So I have some sort of mass going through here. We'll call this Y, and then I'm going to have the rest of it come down here to this step, which is step 3, and this would be 1 minus Y. Okay, so then from my condenser, I am becoming liquid water or saturated liquid, usually about here at 4. You cool it down to saturated liquid. So here's 4 all the way to here, right? So now I am pumping it up to a higher pressure, assuming isentropic, so I'm coming all the way up here. So this is step 5. Now remember, this Y went through to this open feed water heater, and when it's mixing, it's cooling down, and it's cooling down, becoming liquid, and the water here is heating up. So let's put it somewhere here. Remember, just because I put it on the saturated liquid line does not mean it's actually saturated liquid. It depends on the parameters for your system. So these are just general points. So this goes here, this heats up, and this goes to here. So I'm like that, this way, or I'll change that color. I'll go green. Here, 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 and then now I'm at, so this is at 0.6. So I'm right here. I just left my open feed water heater. Now I'm going to go into my pump and be heated again. So here's 7. And then I'm in my boiler, so I'm adding heat, turning it back into saturated, or into superheated steam. So this here is my TS diagram for a general open feed water heater. Now let's go into analyzing each individual parts. Well, I hope you drew this picture. I'd recommend pausing the video if you haven't to draw the picture, because I'm going to be referencing it, but I'm not going to be scrolling up each time, as I have another diagram, this diagram here on my desk. So first things first, let's analyze the high pressure turbine. So let's go back to black. High pressure turbine. Well, so remember first law equals Q minus work dot plus sum M in I H in minus sum M dot exit, mass flow at the exit, enthalpy at the exit. Now, I am not going to rederive how I got this equation. I am going to leave that up to the previous video I did on the first law of thermodynamics. It's probably not my previous, but it's probably like my second or third video. And there I did the derivation for this formula. This is where I'm taking it from. Now we're going to assume steady state, as always. And by the way, for this, I'm going to do the derivation once, and I'm just going to explain the parameters for each part. So 0, steady state. I'm going to assume my turbine is isentropic, so Q is 0. And I do have moving parts, so I have work. So if I solve for work, I get work is equal to sum of the mass flow in, H in, minus sum of the mass flow at the exit, H exit. Well, here I have one inlet, one outlet, so both have the same mass flow rate. So work for the high pressure is equal to m dot times H1 minus H2, high pressure turbine. Now, we're here at state point 2. Let's do the low pressure turbine. So, low pressure turbine. Now, remember, I siphoned some of the mass off, a y amount of the mass off. Well, so everything that goes left through here must be the 1 minus y. So I have to take that into account. Again, turbine's isentropic, steady state. So using this equation here, work of the low pressure turbine is equal to 1 minus y, because it's not the current amount, it's a fraction of my mass flow rate, of my mass is going through my control volume. So 1 minus y times the mass flow rate times H2 minus H3. Again, some of the mass is siphoned off for the open feed water heater. The rest of the steam goes through the turbine, low pressure turbine. So now let's analyze the condenser. So, well, condenser, there's no moving parts, so work will be 0. Work will be 0. I will have heat flow because I'm removing heat from my fluid and rejecting it to my system. And I have mass moving through the control volume, and each mass has an enthalpy value of it. So I have 0 is equal to Q plus the sum of the mass flow rate in, enthalpy in, minus sum of the mass flow rate at the exit, enthalpy exit. One inlet, one outlet for the condenser. So, but it's still that fraction of the mass that was stuffed over. So Q dot is equal to, cold, is equal to mass flow rate of the exit times H exit minus H inlet, which is equal to 1 minus y of the mass flow rate times H4, right? Let's check. Yep, H4 minus H3. Alright, now let's do the first pump. Well, a pump has moving parts, but we're still going to assume there's no heat transfer between the surroundings because this is just the basic understanding of an open feed water heater. So the work of the pump will equal, again, 1 minus y times the mass flow rate of H5 minus H4. No, I'm sorry, H4 minus H5. Now we have to deal with the open feed water heater. This is what's new for this lesson. So each part I'm going to be mainly focusing on what is happening here. Here, let me close this. Alright, open feed water heater. This is what I'm going to be covering here. So I have my open feed water heater. I cannot draw on this tablet. So I have here, which is state 2, and I have y the mass flow rate going in on that inlet. I have 1 minus y of the mass flow rate here at state 0.5, and I'm leaving here at state 0.6. Well, open feed water heater, no moving parts, therefore work is equal to 0. And the open feed water heater, which, like I said before, the only heat transfer is inside the control volume itself between the steam and the water. There is 0 heat transfer between the system and the surroundings. There's no heat leaving this system, no heat entering the system. So Q is also 0 because Q dictates how much energy leaves the system and how much energy enters the system, and that doesn't happen. So I have 0 is equal to sum of the mass flow rate of the inlet, enthalpy inlet, minus sum of the mass flow rate at the exit, enthalpy of the exit. So set M equals sum of the mass flow rate of the exit, enthalpy of the exit. Well, what's my entrance? At state point 2 and state point 5. So my mass flow rate at state point 2 is ym dot h2 plus 1 minus ym dot h5 is equal to m dot h6, because remember, whatever's going in has to come out. If I have one exit, that means that is my mass flow rate, because this 6, if you recall, is the main pipeline that goes through the entire system. The masses were separated here at 2 and 5, or 2, and they come back together at 2 and 5, and the open feed water heater. So this mass flow rate cancels out, and I get yh2 plus 1 minus yh5 is equal to h6. Now, with this equation, you can determine the state point of h6, h2, or h5, or y, depending on what you are looking for in your problem. I can't tell you what you're looking for until you get the entire problem back. I've had problems where I'm looking for how much mass was diverted based off these enthalpies. What's my enthalpy of 6 after I go through the entire system to solve all this information? What was my pressure at state point 2? You don't know that but you can with this system, or with this equation here that we just got. Alright, so next is the second pump. Like the first pump, it is equal to m dot of inlet minus outlet. And then boiler, it's a boiler and pumping heat into the fluid. No work going on. Q is equal to m dot of exit minus inlet, like up here. So H1 minus H7. And this boiler will be less because the water is already preheated after going through the open feed water heater. So now let's find my efficiency. Well, if you recall, that's work net over Q in. Well, my work net is going to be the work of the high pressure turbine plus the work of the low pressure turbine minus the absolute value of the work of the pump 1 minus absolute value work of pump 2 all over Q hot. Now I have this absolute value here for your benefit to not to confuse you. Whenever I'm solving it, I leave the pumps as a positive number and I simply write, say, for out, like pump 2, or I'm sorry, in. I would say 5 kilojoules of work pumped into the system type deal. So I know, okay, that's going into the system. I have to deduct that from my efficiency. But this is how you analyze an open feed water heater. It is the same here for the boiler, the high pressure and low pressure turbine, the condenser, the pump. Like I said, I'm going to divert some of the steam into my open feed water heater, so there's going to be less steam going through my low pressure turbine. This steam preheats the water coming out of the pump. Everything leaves as liquid water and goes through the second pump, and it is pumped back up to the boiler. And these are how you would analyze the control volume first law of thermodynamics for each component. If you have any questions at all, please post a comment and I'll answer it when I can. I'm going to turn this into a two-part episode because this is at 20 minutes already. So this will be open feed water heaters. And lecture 9 will then be closed feed water heaters. But these lectures will be uploaded back to back. So you don't have to worry about waiting a couple days. Have a good night. I'll see you in lecture 9.